la vérité.
In all previous tests, I defaulted to using rounded wingtips, but this is actually a blind spot in optimization. In this video, we will bridge this cognitive gap through in-depth comparative testing. Some might think that for a full-scale wing with a 14-meter wingspan, adjusting the wingtip shape is just a minor tweak, with little impact on overall aerodynamic performance. However, this intuition often masks an aerodynamic truth. The wingtip is the throat of aircraft performance. Every subtle change in wingtip configuration directly alters the intensity and evolution of wingtip vortices, significantly affecting induced drag and ultimately impacting the lift-to-drag ratio of the entire wing. These seemingly insignificant changes often determine the ultimate limit of flight efficiency. In aerodynamic design, engineers have developed various wingtip configurations to effectively reduce wingtip vortices and induce drag. To ensure the scientific rigor of this experiment, I will strictly follow the single variable principle. While keeping the main wing design identical, I will only reconstruct the geometry of the wingtip. This test uses the basic cut or square tip as a baseline and focuses on evaluating the performance differences between the Hoerner-tyoe, the rounded tip, and the rake tip. Additionally, considering this project focuses on small electric aircraft and balancing structural weight, manufacturing complexity, and aerodynamic gain, we have temporarily excluded winglets from this test to explore the limits of wingtip geometry optimization in non-winglet architectures. First is the rounded tip. In terms of design, to minimize flow separation and reduce pressure drag, while considering the geometric continuity of the thin trailing edge, I set the start of the arc behind the chord line. This approach ensures that airflow passing over the wingtip transitions smoothly from the wing surface to the tip, avoiding abrupt separation at sharp edges, thus improving aerodynamic smoothness during low-speed flight while maintaining structural rigidity. Next is the Hoerner wingtip. This classic configuration uses a contraction design on the lower side of the wingtip to effectively alter pressure distribution. It blocks the high-pressure airflow from rolling over the wingtip to the suction side, creating a counter-rotating micro-vortex at the wingtip edge, which offsets the intensity of the main vortex. For small aircraft, the Hoerner-tyoe not only provides significant drag reduction during low-speed cruise, but its unique geometry also grants the aircraft better stall characteristics, making flight more stable. Finally, the rake tip. This design introduces a significant sweep angle at the wingtip, effectively extending the wing's effective aspect ratio and making the lift distribution closer to an ideal elliptical distribution. The core advantage of the rake tip is its ability to push the generation of wingtip vortices backward and outward, significantly reducing induced drag. Especially in high-speed flight conditions, this strategy perfectly balances structural weight and aerodynamic efficiency, making it a highly potential comparison configuration in our test. Given the swept configuration, the rake tip area is slightly larger than other tips, which provides a certain enhancement to the results. After finalizing the models, I imported them into Star CCM Plus for high-precision aerodynamic simulation. To ensure rigor in comparison, I performed a full-range performance scan of the 4 wingtip configurations under identical flow environments and boundary conditions. This test covers an angle of attack range from 0 degrees to 17 degrees, tracking the evolution of key parameters such as the lift-to-drag ratio and total drag coefficient. By capturing dynamic aerodynamic data across these multiple conditions, we can clearly quantify the actual performance of each design from level flight to near stall conditions, revealing the macroscopic performance differences caused by design tweaks. Next, we analyze the key aerodynamic efficiency metrics. The performance of the configurations from best to worst is raked, rounded, cut, Hoerner. Although theoretically the Hoerner wingtip should be superior to the cut, its performance in this model did not meet expectations. The raked tip, due to its larger additional lifting area, has significantly higher aerodynamic efficiency than other configurations. The rounded tip outperforms the cut baseline in maximum lift-to-drag ratio, as well as in average lift-to-drag ratio at both low and high angles of attack. The reason is that the rounded configuration effectively weakens the wingtip vortex intensity, maintaining excellent drag characteristics, CD, while improving the lift coefficient, CL. Further comparing aerodynamic efficiency at the same lift coefficient, interpolation analysis shows at CL equals 0.6, the configurations from best to worst are raked, rounded, cut, Hoerner. When CL increases to 1.0, the performance of Hoerner and cut tends to equalize. In longitudinal stability analysis, the pitching moment coefficient of the rake tip is over 12.9% higher than that of the rounded configuration. A higher value means the aircraft produces a stronger pitch-up tendency in flight. This change in aerodynamic characteristics not only increases the structural load on the wing root, but also places higher demands on the trim capability of the horizontal tail, thereby increasing the control burden on the elevators. In contrast, the differences in pitching moment among the Hoerner, rounded, and cut configurations are relatively small. Regarding simulation accuracy verification, this calculation used the SSTK omega/gamma array theta transition model. Statistics show that the average wall dimensionless distance, y+, is kept within 0.7, indicating that the first layer of the mesh on most of the wing surface is within the viscous sublayer. This allows for direct resolution of velocity gradients near the wall, rather than relying on wall functions for estimation, significantly enhancing the reliability of the calculation results. Simultaneously, the maximum y+ value is controlled within 1.6, fully meeting the grid requirements for low y plus SST models, ensuring high confidence in the simulation data for boundary layer flow capture. Regarding the phenomenon where the Hoerner wingtip underperformed, after reviewing the simulation parameters and classical aerodynamic theory, I found that this configuration is extremely sensitive to the fidelity of geometric details and grid resolution accuracy. The core design logic of the Hoerner wingtip lies in using a sharp lower edge to force specific airflow separation, thereby weakening the wingtip vortex. At a 10-degree angle of attack, by comparing the flow fields of the Hoerner and cut wingtip configurations, it can be seen that the Hoerner tip exhibits more complex local pressure gradients, reflecting significant airflow disturbances in the wingtip area. Further flow visualization shows that compared to the cut baseline configuration, the Hoerner configuration's wingtip vortex intensity is more severe. This strengthened vortex structure directly leads to an increase in induced drag, which intuitively explains why this configuration performed poorly in terms of drag in the current simulation model. After reviewing the geometry of the CAD model, I found that the curvature setting of the wingtip chamfer transition area was too smooth, and there was significant bluntness on the lower side of the leading edge. This geometry directly weakened the forced airflow separation mechanism of the Hoerner wingtip configuration, preventing the airflow from achieving sharp separation at the predetermined location, thereby losing the core-induced drag suppression capability of this configuration, which directly caused its simulation performance to not meet expectations. To verify the impact of geometric fidelity on Hoerner wingtip performance, I plan to perform geometric iterations on the current model by constructing two sets of models with thinner edges that are closer to the theoretical design, and conducting comparative simulation calculations to quantitatively evaluate the aerodynamic gain after geometric correction. In the first optimization model, I focused on thinning the wingtip side edge, strengthening sharpness. Combined with literature analysis, this can force the airflow to separate at the wingtip position, thereby effectively reducing induced drag. In the second optimization model, I further enhanced the sharpness of the leading edge, making the sharpness of the front and rear edges of the wingtip basically the same, thereby minimizing potential interference of geometric morphology on flow transition. This improvement aims to quantitatively evaluate the separation threshold of leading edge bluntness on Hoerner wingtip aerodynamic efficiency by constructing the edge morphology closest to ideal theory, thereby identifying the root cause of why previous simulation data did not meet expectations. Finally, these two optimization models were added to the calculation matrix to compare the results of all 6 models. Under 5 degrees angle of attack conditions, the H2 model's lift-to-drag ratio reached 25.67, an increase of about 4.3% over the baseline Hoerner, 24.61. More importantly, this improvement was not at the cost of lift. Its lift coefficient was about 0.617, basically on par with the baseline configuration. This powerfully proves that this optimization successfully achieved pure drag reduction, rather than sacrificing lift to make the data look good. At 10 degrees angle of attack, the optimization effect is equally significant. H2's lift-to-drag ratio reached 22.68, an increase of about 5.4% over the baseline of 21.52, and even exceeded the rounded tip, 22.09, by about 2.7%. These data indicate that after geometric detail correction, the Hoerner wingtip's applicable range is no longer limited to specific high angle of attack intervals and possesses significant efficiency advantages even in normal positive angle of attack ranges. At the critical 16-degree angle of attack condition, the H2 model's comprehensive performance is particularly outstanding. Compared to the rounded tip, its lift coefficient increased by about 4.3%, drag coefficient decreased by about 4.2%, and the final lift-to-drag ratio increased by 8.9%. This double lift increase and drag reduction optimization is not a simple parameter superposition, but strongly proves that the H2 geometric modification successfully improved the local flow field structure at the wingtip under high angles of attack, enabling synergy between induced drag reduction and lift potential release. Overall, the H2 model shows consistent improvements at angles of attack of 5 degrees, 10 degrees, and 16 degrees. At low incidence, it mainly reduces drag. At moderate incidence, it increases aerodynamic efficiency, and at high incidence, it simultaneously increases lift and reduces drag. The H2 geometry therefore improves overall aerodynamic performance across a wide range of angles of attack. Of course, exploration in engineering design is endless. Although the current results are logically self-consistent and show significant gains, there is still room for optimization. For example, this simulation has not yet incorporated the complex interference of external loads such as wingtip navigation lights on the local flow field. Furthermore, as a phased achievement, while the H2 configuration has outperformed the rounded tip and baseline cut configurations in performance, it is far from the end of performance limits. These unsolved variables are the research directions for our subsequent deepened design. Thank you all for your continued attention and support. Apologies for the fluctuation in update frequency recently. As the project progresses, the channel will gradually resume normalized updates, and we will continue to dig deeper into the mysteries of aerospace design. Stay tuned.